All right, so Newton's first law can be summarized in one word. Inertia. Okay, which is a single one-word way of saying this. An object at rest will remain at rest. An object in motion will remain in motion at a constant velocity unless acted upon by an external unbalanced force. Inertia is better, much shorter, okay? But that's what it means, okay? So really, what Newton's first law says is that this chair will stay right where it is, provided nobody pushes it. Well, duh. Okay? Of course it's not going to go anywhere if nobody pushes it. Okay? That's just simple physics. Newton's first law, while not rocket science in terms of difficulty, is still part of rocket science. Okay? But it's pretty simple. Okay? But the other part of Newton's first law is the part that we have to be most mindful of in real life. And that is the part about an object in motion will remain in motion at a constant velocity unless acted upon by an external unbalanced force. What that means is, if something is moving, it will continue to move unless something tries to either accelerate it, okay, positively, or accelerate it negatively, or even just turn it. Even a change in direction would count as an external unbalanced force. This is why it is the law to wear your seatbelt in a moving vehicle. The seatbelt is the single greatest invention to thwart Newton's first law. If you are wearing your seatbelt and your car stops suddenly, your seatbelt will stop you. Not quite as suddenly, but quite suddenly. Okay, has anyone ever been in an accident? You know, you get like this nice bruise right across your chest, exactly the same shape as your seatbelt. Okay? You also get bruises on your arms if you're the driver because the airbag blows your hands to the side really forcefully. Okay? But without your seatbelt, Newton's first law will apply. You will continue to move at whatever velocity you are moving at until acted upon by an external unbalanced force. The first unbalanced force is often the windshield, which won't stop you. Okay? It'll severely injure you, but you would probably go through it if you were moving more than about 60 kilometers an hour. Okay? Which then means you will be slowed down or acted upon by other forces outside the vehicle. Those are arguably as bad or worse. Okay? Because they could include the other vehicle, the road, okay? Things like that. That is why you are supposed to wear your seatbelt. Okay? Your seatbelt stops you. If you continue to move, you will get hurt. Okay? And I know this is always when somebody points out, well, you know, there was that guy whose car rolled over and he got thrown out of it and he lived. Yeah, that's like, that guy needs to buy a lottery ticket right that day. Okay? Because the odds of that happening are so slim. Okay? You are almost always better off. Okay? And by almost always, I mean basically always better off to be in the car. Okay? Now, here's the weird thing about all of your safety equipment in your car. It's all designed around Newton's first and second laws. Okay? The first law stuff is designed to stop you and keep you from continuing to move. Okay? That would be your seatbelt, your airbags, okay? You know, things like that. Anything that's going to keep you from continuing to move forward. All right? That's the first part of safety. The second part of safety has to do with your acceleration. Okay? And that's a little bit to do with Newton's second law, but we'll talk about it anyway. We're all familiar with this formula. Okay? Most of the safety mechanisms in your car work around that formula, believe it or not. Okay? There's not much that we can do about this part of the equation. You've either slammed on your brakes to slow down before the crash, or you haven't. Okay? There's not much we can do about that part of it. Once the collision has occurred, okay, that part of the equation is pretty much fixed, although it can be dependent on your mass. We'll talk about that in a bit. The rest of the safety devices in your car focus on this part of the equation. do they want to make T bigger or smaller?
Bigger.
Bigger. The longer the crash can take, the better off you will be. It's counterintuitive, like, oh, I just want the crash to be over, okay? And it is like that usually, okay? But we're talking hundredths, and if we're lucky, tenths of a second difference, okay? If we can make the crash take hundredths to even tenths of a second longer, then this number goes down. It's that number that hurts you, okay? Because that number is related to this. The greater your acceleration, the greater the force. Okay? That's what's going to hurt you. So we want that acceleration to be as low as possible. That's why your car is designed to have crumple zones. Okay? Modern cars are designed to self-destruct in a crash. Okay? They crumple up like a tin can. Okay? They blow up because they're full of airbags. Okay? Like it turns into like a cannoli. Okay? When you get into a crash, you're just surrounded by all of this, like, you know, inflated bags and things like that. Okay? All of that is designed to keep you safe and to make the crash take longer. Okay? Before that, people got hurt a lot more severely. Airbags, for example. Yeah, well, let's start with seatbelts. So your seatbelt, it jerks you to a stop. Okay? But believe it or not, your seatbelt actually stretches a little bit. If you're getting a crash going more than 50 kilometers an hour to the point where your airbags would deploy, your seatbelt will also have to be replaced. They stretch, okay? And that's designed to help you slow down a little bit more slowly. Once they've stretched, they can't be used again, they have to be replaced, okay? So they stretch a little bit, not a lot, okay? Then you've got your airbags. Is hitting an airbag better than hitting the steering wheel from your head's point of view? Definitely, okay? Now, don't get the idea that an airbag is a pillow, okay? It's a punch in the face. Okay, the thing inflates so fast. It's an explosion. Okay? People's ears ring because of these things afterwards. All right? But it's a lot better than getting the steering wheel right here. Okay? People in your parents' generation, even some people in my generation, a lot of them that were in car accidents have the same scar. It runs right across here. It's the steering wheel scar. Okay? You get in an accident, your head goes forward, and it would hit this rigid, hard piece of wood or metal or both, okay, that was the steering wheel, and it would literally scalp you, okay, it would peel back your scalp, okay, because the cars were made not to be safe, per se, they were just built to be strong, okay? And so when you would hit the steering wheel, you'd get head injury, concussion, okay, stuff like that. It wasn't good, right? Before airbags were invented, they actually designed steering wheels so that they would collapse. And they made them a bit fatter and more cushioned, but they would also cave in if you hit them. Right? You could actually hit them with your fist and cave them in. Road rage was bad for collapsible steering wheels. Okay? So they would cave in, so it would, you know, prevent some of the head injuries. But in airbags, even better. You hit the airbag, your head slows down. Okay? It takes longer to go from VI to VF. T is greater, A is smaller. Okay? Everyone kind of follow me there? All right? So airbags are good that way. Okay? They help to slow down, make the crash take longer. Okay? The crumple zones do the same thing. They help the crash to take longer. Okay? That keeps you safer. Right? All of those things are really, really important, okay, when it comes to saving your life. Okay? Are you good with that? What determines whether your airbag goes on or off? Like if you get in a crash, do your airbags always go off? Nope. Okay? Your airbags do not always deploy. Okay? If you're going faster than 50 kilometers an hour, they're probably going to deploy. Okay? Unless there is a significant difference in mass between the two vehicles. Okay? So this is the safety feature that's never talked about. Okay? Everyone talks about brakes and seatbelts and airbags and all these other crumple zones and all of that. But there's one safety feature you either have or you don't. Mass. Okay? If you are the more massive vehicle, you're going to win. Okay? In every crash, there's a winner and a loser. Make no mistake, there's very rarely a tie. Okay? In every crash, there's a winner and a loser. The loser's the one that goes backwards at the end. Okay? You don't want to be the loser in a crash. Okay? Because if you're the loser in a crash, this number is positive and this number is negative. If you're the winner in the crash, this number is positive and this number is positive, and you win. Okay? which means you have less acceleration because your change in velocity is less. Think about a semi-truck colliding with a smart car. Okay, we know who wins that one. The truck, every single time. Doesn't matter how fast the smart car is going, unless it was going like the speed of light, and then it would make a difference. But okay, otherwise, it just doesn't have any mass. Okay, it just doesn't have enough of it. So its acceleration is always going to be bigger because it's the smaller of the two vehicles. Okay. Now, a few years back, we actually had a collision, okay, in our SUV. We had a Ford Expedition, a big, heavy SUV. Okay, and this lady turned left in front of us for whatever reason. She didn't see the big, giant blue truck bearing down on her. Probably. Okay. Anyway, she turned left right in front. I didn't get a chance to hit the brakes, and we plowed right through that car like a hot knife through butter. Okay, we'll win. Okay? I'm very competitive. Right? In a crash, I want to win. Okay, I mean, we pushed that car right through the intersection. Okay, and we're continuing to move forward. Her airbags all deployed. Okay, car was a write-off. Okay, and I'm like, well, we're gonna have to replace that headlight and maybe the fender. And no airbags deployed in our car, because the acceleration we experienced wasn't great enough to deploy the airbags. Winning. Okay, so it's all about that acceleration. Okay, Newton's first law also has to do with mass. Okay, the greater your mass, the greater your inertia, the greater your tendency to keep doing what you were already doing. Okay, it's why you've never seen a skinny sumo wrestler. Okay, they just never win. Okay, it's very easy to make something with very little mass change its speed. Okay, if the big guy came running at him, that would be it. Okay, does that sort of make sense? Okay, so mass also affects your inertia. The bigger you are, the more inertia you're going to have, and the greater your tendency to keep doing what you were doing will be. Okay? All right. So, now, the word force. Okay? Force, very simply, is a push or a pull. Okay? You can do one or the other, okay, with a force. A force cannot be both a push and a pull, okay, in any given situation. So a force is a push or a pull. It is a vector quantity. It has magnitude, that is how hard you push in newtons, and direction, whichever way you decide you're pushing the object or pulling the object or whatever. Okay, so force is a push or a pull, okay, and it is a vector quantity. So if I'm looking at these situations here, okay, so if the tow truck is pulling this car, okay, so let's say the tow truck is just pulling away from a stoplight. Okay. The force it's exerting is angled. Okay. But the car is only going to move horizontally. The tow truck's no longer trying to actively lift it off the ground, it's just hanging there. Okay. The truck pulls it forward, the car moves forward. Okay. It's still exerting some force vertically, but that's just to offset gravity and keep it from falling down. Okay, so forces have vertical and horizontal components. Okay, when we're talking about a projectile, the reason it has that arc that we talked about in the last unit is because gravity is constantly pulling it in the same direction, causing an acceleration in that direction. Okay, all right, and then obviously if you want to knock something down, you push on it. Okay. Now, I want you to think about this whole thing about an object in motion remains in motion unless acted upon by an external unbalanced force. We talked about how that affects you in a car crash. Okay? It's also why motorcycles are much less safe. Okay? They have less mass and, well, there's no seatbelt on a motorcycle. Okay? But it's also a big concern if you're an astronaut. Okay? If I'm on the International Space Station in zero gravity, and I get moving, how do I stop? It doesn't do me much good to flail my arms, and I'm not going to fall to the ground. Okay? There's no gravity to pull me down. Okay? Unless I can grab onto something, I'm going to keep floating along through the tube, okay, in the space station. It's even more dangerous if I'm outside the space station. Okay? So when the astronauts are doing an extravehicular activity, they're working on something outside the spacecraft, they have to be very, very careful. If they become dislodged or disconnected, and they have no way to maneuver, they'll float away. Okay? Now, most suits have what we call reaction control systems, RCS. They're little jets that are filled with gas, okay, like it actually comes out of your breathing tank. Okay? And you can trigger which ones fire, and when they fire, they push you. Okay? So if I wanted to move forwards, I would fire the ones on my back. They would push me forward. But if those run out of fuel and I'm moving, what's going to happen to me? I'm not going to have any way to stop. I'm just going to float away. That'd be bad. Okay? And floating into eternity would really suck. Okay? Eventually you're going to run out of air or something. That's not going to be good. Okay? So they have to always be very mindful of how much of that maneuvering gas do I have left, or they're just tethered to the spacecraft. Okay? Things like that. So I'm going to show you a video. Okay, so this is dash cam footage of a wreck that my cousin was in. Okay, so she is in the car in front of this Nissan Altima. Okay, a distracted driver is going to come in from the left. Okay, in a fairly large full-size SUV, and she's driving like a small sedan, probably no bigger than this thing here. Okay, and you can see kind of what the effect of mass is, okay, on this crash. Okay, now she ended up with a broken pelvis, broken femur. She was pretty severely injured in this crash. Okay, had this car not also entered the intersection and clipped that truck, she probably would have been killed. Okay? But you could see that even though that guy did finally hit the brakes right about here when he saw this car, okay, it wasn't enough to stop him. And when he hit her car, he pushed her quite a ways. Right? In fact, what really stopped them is these orange plastic containers. Okay? You don't actually see it so much in the crash, okay? But in Hawaii, where this happened, those orange plastic containers are actually full of water. Okay? In Canada, we can't do that because most of the year they're just as hard as concrete anyway. Right? So in Hawaii, where they're going to be above freezing all the time, they're great. When you hit them, they just rupture, okay? And they slow you down. It's almost like a cushion. So anyway, he hit her, moved her quite a ways, but I mean, talking about a difference in mass, this is, I think, like a large Toyota Land Cruiser or something, okay, a fairly large vehicle, okay, versus her small, I don't know, Chevy Cobalt or whatever that was that she was driving, okay, difference in mass, right? Winner and a loser in that crash. Okay. All right, oh, and then I'll show you the smart car crash in a little bit. Okay, so mass, we got to understand, mass and weight are two different things. Okay, mass is a measure, of how much matter you are made up of. Weight is a force. Specifically, it's how much the force of gravity pulls on your mass. Okay, so this is another thing we do terribly wrong in most Western societies. Okay, someone comes up and says, you know, how much do you weigh? First off, you should never do that. It's really rude. Okay, but if someone comes up and asks you how much you weigh, what do you tell them? You don't have to give me a real number here, but you tell them how many kilograms or how many pounds, right? Well, that's not weight. That's your mass. Okay? Well, we interchange weight and mass in Western society all the time. They're not the same thing. Okay? What I do if someone asks me how much I weigh is I tell them. Okay? I tell them I weigh 785 newtons. And they usually chuckle awkwardly, shuffle their feet, and look for someone else to talk to, which is perfect because they were rude to ask that question in the first place. And secondly, I'm not a big social person, so I'd rather just not talk to somebody. Okay? So if I tell them that, the benefit is I actually told them the truth. That is how much I weigh. But it's a meaningless number to them because they have no idea what that means. Okay? My weight is how much gravity pulls on me. It's what you would feel if I stood on you or sat on you. That's what you would feel. You don't feel my mass. You feel my weight. Okay? So if I go to different places my weight can change. Even different places on Earth, I'll weigh more or less because the acceleration to gravity is different depending on where I am on Earth. Okay, if I go to the moon, that's the greatest weight loss plan ever. I'll weigh 1/6 of what I weigh here. There won't be any less of me. My clothes won't fit any better. Okay, I'll just weigh less because there's less gravity there. Okay, if we want to gain weight or lose weight, we have to lose or gain how much of us there is. That's mass. Okay, but mass doesn't sound as good. Okay, nobody wants to join a mass loss program. Okay, or hey, I gotta bulk up. I gotta put on some mass. Okay, sometimes we'll say muscle mass. Okay, we'll say that, but okay, most of the time we use the word weight incorrectly. Okay, weight is how much the gravity pulls on your mass. Okay, now is it directly tied to your mass? Yes. The more mass you have, the more you weigh. Okay, in that specific place. Okay. All right, so mass has to do with how much matter you have. The bigger something is, generally, the more mass it will have. Okay, so the supertanker has lots of mass. There is a lot of matter there, lots of atoms and molecules and all of that kind of stuff. There's a lot of it. Okay, versus this penny, okay, which has very little mass. Okay, if I flick this penny, it's going to really move. If I flick this ship, nothing's going to happen. Okay, because it has more mass, and as a result, it has more inertia. Okay, we're back to this thing with the car crash there. Okay, more inertia, more mass means you continue to do what you were already doing, okay, a little better than something else. Okay, everyone all right with that idea? Okay, so mass matters. Okay, and mass is a scalar quantity. Okay, I don't say my mass is 80 kilograms down. Right? My mass is how much of me there is. Okay, I wish there was less of me, but you know, that's what I got to deal with. Okay, as you get old, your metabolism slows down. Okay, but it's how much of me there is. It's a scalar quantity, and it'd be the same no matter where I go. But my weight, 785 newtons down, okay, is a vector quantity. Gravity pulls me down. Okay, therefore, that has magnitude and direction. Okay. If we want to calculate weight, we calculate the force of gravity. This formula is on your formula sheet. The force of gravity is mass times the acceleration due to gravity. So if you want to play that joke on somebody that I just told you about, okay, you take your mass, you multiply it by 9.81, and you know your weight in newtons. Okay, you can tell somebody how many newtons down you weigh the next time someone asks you that very impolite question. Okay. All right, so mass is scalar, it's how much of you there is. Okay, weight is a force. Okay, so when we go and say, I gotta go and lift some weights. No, you're going and lifting masses. Okay, it doesn't sound right, but that's what you're doing. Okay, do they have weight? Yes, they do. Okay, but they only have weight because they have mass. All right. Okay, so Newton's first law, there's a lot of Newton's first law stuff in winter sports, okay, because we deal with ice surfaces, which are, you know, very low friction situations. So if you like paint drying and curling, okay, you can see that a lot in curling, okay? When you slide the rock down the ice, right, it doesn't slow down very much. Its acceleration is very low because there's very little friction between the rock and the ice. In fact, much of curling is changing where the friction is and how much of it there is in order to steer the rock to where it needs to go. Okay? How many people have ever watched that? Yeah, it's that boring, isn't it? Okay, so when you watch curling, I know I just kind of make fun of curling because I like making fun of it, but in curling, you can spin the rock different ways, right? You can do an outturn, or that's an inturn and then an outturn, okay? And that'll result in the rock spinning, okay? And when the rock is spinning, it'll kind of curl on its own, okay? But the people sweeping it can also steer it, and not by like pushing it with the broom, because apparently that's illegal, okay? So what you do instead is you sweep in front of the rock or on one side of the rock, like kind of in front and to the side a little bit. And when you do that, you melt the ice. That's why curling ice has all the little bumps on it. Okay? When you sweep, you melt some of those little bumps. and you lower the friction because now there's a layer of water between the rock and the ice, and it lowers the friction. That's why it can travel farther. Or if you want it to turn to the right, you sweep it a little bit on the left. Then there's more friction on the right, and it'll naturally slow down and curl that direction a little bit. Okay? That sort of makes sense? Now, if I was on a perfectly frictionless sheet of ice that was infinitely long and I pushed that rock, it would go forever. Or if I had that rock in space and I just gave it a little push, it would go forever. Okay? Ice hockey, okay? Same thing. If you're that guy, you know, waiting there at the top of the, you know, at the hash marks for the one-timer, okay, the puck is going to come straight to you. Okay? It's just going to slide in a nice straight line, unless somebody made it spin or something. Okay? It's going to come to you in a nice straight line. You just have to wait. Okay? There's nothing there that's going to stop it from doing that. Okay? Okay, here's another one. Anybody ever do the magic trick where you pull the tablecloth out from underneath all the dishes? Anyone ever seen somebody do that? Okay? It's a trick, but not really. It's not magic by any stretch of the imagination, but you got to do it right. Okay? Most people do it wrong. They take the tablecloth and roll it into their hands, and then they do this. And they lift it up, and all the dishes are everywhere. Okay? If you want to do that trick and actually have a chance at it working, which way do you pull?
Down.
Down. Okay? You don't even pull straight out. Okay? You're never going to be perfectly straight. You roll that thing up and you put your knuckles against the table and you push it straight down. Then the tablecloth slides straight towards you. Okay? If the stuff that's on the tablecloth is heavy enough and has enough inertia, it'll stay put. Okay? That's what you're trying to do with that trick, is use the inertia of the dishes. Their inertia is that they're not moving. They want to keep doing that. That's what Newton's first law says they should do, is stay put. Okay? So if I have a low friction tablecloth and fairly heavy dishes, I'll easily be able to pull that tablecloth out from under the dishes. Okay? That sort of makes sense? Okay? You can do the same thing. If you got poker chips at home, okay, you can make like a stack of them and then flick one at the bottom of the stack. If you do it right, you can knock the bottom one out. The stack will stay, like it'll fall down, but it'll stay in that spot, because you didn't change the inertia of the rest of the stack. All right? Here's another one. It's a weird one, but it's true. Toilet paper. Okay? It's got the little, you know, perforations on it so that it tears easily. Okay? If you have like a full roll of toilet paper, it's easier to just pull it and have the perforations tear off, because there's all that mass still on the roll. Okay? So it's more likely to stay put. If you're less than halfway, with less than half of it left, and you try that, you're probably going to have the whole thing on roll on. Okay? You can try it at home sometime when you're bored and, you know, in the bathroom. Okay? You can try that, but it's a Newton's first law thing. Okay? Full roll, way easier to tear a sheet off of without holding the roll. Okay? Try it without holding the roll, and then you probably have to clean up. But yeah, it's fun. You can try it. It's physics. Okay, so we use this term, net force. Okay, net force is the vector sum of all the forces acting on an object. Okay, there's almost never a situation where only one force acts on an object. Okay, so I'm going to give this chair a push. Okay? I want you to think about how many forces are acting on the chair in the moment I'm pushing it. So while I was pushing it, did it accelerate? It did. But once I stopped pushing, it actually started to accelerate the other way. Would you agree? Okay, while I was pushing it, how many forces were acting on the chair? Was I acting on the chair? Okay, that's one. What else was acting on the chair?
Gravity.
Gravity. What else?
Air resistance.
Yeah, friction. We'll just say all the frictions. Air resistance, flow resistance, all the frictions. The hardest one is the last one. Sam mentioned gravity. He's 100% right. Something's got to be offsetting gravity, though, because otherwise the chair falls through the floor.
I was gonna hit the floor.
The floor, yeah. We call it normal force, but it's the force of the floor pushing back up. Okay? There are actually 4 forces acting on the chair in that situation. 2 of them cancel out. The chair didn't move vertically, so the force of the floor and the force of gravity canceled. Okay? They weren't part of the net force. Okay? But the chair did accelerate that way, which means my force was greater than the frictional forces that were acting on it while I was pushing it. Okay? So there was a net force that way. Once the chair left my hand, now there's no force from me. Gravity and the floor still cancel, but friction is still present. So what did the chair do? Was there an unbalanced force on the chair? Right? Gravity and the floor canceled, so they were balanced. The only force left was friction. That's why the chair slowed down. There was a net force slowing the chair down at that point. This is the challenge in Unit 2, is being able to look at a situation and identify what forces are acting on an object and what are they doing to it. Okay? That's the real challenge there. So if I've got something as simple as I'm sliding a book along a table, okay? I've got gravity in the table, but they cancel. Okay? And then I've got friction and the applied force of the thing pushing it. Okay? If the applied force is greater, then the object accelerates. Okay? Is it possible for me to push on something and have it not move? Yeah. Okay? Which means then that the net force in that situation would be 0. Okay? This comes back to Newton's first law. Okay? Newton's first law says an object at rest remains at rest unless acted upon by an external, unbalanced, or net force. The net force is 0. The object is going to do one of 2 things: not move, or move at a constant velocity. As soon as you have a net force, then there's going to be an acceleration. That's Newton's second law. Okay? Everybody okay with that idea? Okay? So Newton's first law deals with all the situations where all the forces are balanced. Okay? In those situations, an object is either not moving or it's moving at a constant velocity, which, remember, would mean it's moving in a straight line as well. Okay? Because velocity is a vector quantity, yes? It's actually possible to move at a constant speed and be accelerating. We'll learn about that in Unit 3. Okay? Velocity is a vector quantity, so constant velocity means straight line. Okay, so inertia and mass, okay? If I've got those items there on the right, okay, obviously the smaller ones are easier to change, okay, than the bigger ones. Okay? They have less inertia because they have less mass. Okay, so I'm going to show you these videos here, these crash tests. Okay, when we're looking at the book, okay, when we're drawing a diagram of the forces acting on an object, we draw what we call a free body diagram, okay, which means, come on, I draw a box, okay, that represents the mass, and I would write the mass inside of it, like 2 kilograms, and then I draw the forces that are acting on it. Okay? And that allows me to figure out the net force. In this case, the net force is 2 newtons forwards. Okay? Everyone all right with that? Free body diagrams require no artistic ability whatsoever. It's a box. Everything is a box. Okay? A cat, a car, it's all a box. Okay? For free body diagrams. Right? So they're pretty straightforward. Okay, so the way some of the safety features in your car work also relies on Newton's first law. Okay? Your seat belts, okay? They don't always latch. They only latch when you're like in a hurry and you're trying to, and then, you know, you're frustrated because you're trying to pull it out quickly, but it won't come out. Okay? What you've usually done in that case is you've actually jarred the full locking mechanism. Okay? But the way that your seat belt works is you have that ratcheted wheel, you have a locking bar, and then you have a small pendulum. Okay, it's all built into the inner workings of the seatbelt. So when you're driving along at highway speed, you can grab onto the seatbelt, or even like town speeds, grab onto the seatbelt and kind of adjust where it's sitting and it'll come out. Okay? But if you get into a crash, it'll lock. Okay? And the reason it'll lock is because the locking bar is actuated by a pendulum, which in a crash must move forwards. Okay? If your car stops suddenly, that pendulum keeps going forward, according to Newton's first law. Okay? And because it does that, it tilts up and rotates the locking bar into position, preventing your seatbelt from unrolling. Okay? That sort of makes sense? Simple. Newton's first law application. Okay? We know the pendulum can do nothing but continue to move forward in that situation. Okay? Airbag sensors work similarly. Okay? The first airbag sensors were actually contact activated. Okay? So if you got in a crash, the switch would be activated when pieces of the car would close the switch, okay, close the circuit. But now they're actually on an accelerometer, which is very much like the one inside your phone that tells you which way you're holding it. Okay? It's kind of a metal ball inside a cage of wires. Okay? So when you're driving along, the ball sits in the middle and doesn't touch anything. Okay? But under enough acceleration, the ball will move forwards because of Newton's first law and touch the wires at the front. If it touches it, it completes the circuit that detonates the airbag. Okay? But no one's going to be able to walk up to the front of your car and hit the bumper and set off your airbags, which could happen in the first generations of airbags. Okay? Sort of makes sense? So now they work on Newton's first law as well. They're not going to go off unless sufficient acceleration is produced. Okay? All right. Now I'm going to show you this smart car.